So now that we all know why we are here today, let's begin our first phase of the workshop to know about the role in AI design and development. So let's take a look at a high-level overview of how machine learning works. As an engineer or data scientist or AI researcher or developer, there is actually a lot that you are responsible for when it comes to collecting and cleaning, training data, building and training your models, and deploying it, and much more. But we are also human, meaning we both intentionally and unintentionally shape every facet of machine learning, because we are also the ones who choose the data sources, determines the evaluation metrics, and all of us get affected by the results. You are going to see this diagram throughout the workshop as we work through exercises to take you through each phase of this process. Now let's get started. There are actually educational resources at the end that you can use and take to learn more about neural network and AI design. Also, it's normal for many of these concepts to seem complex at first. They usually take a couple of months to learn, and that's okay. Let's dive in and get started. So we need to go to this link so that whenever I am running any cell and the code with the notebook, you can do the same and also check how the coding is working. So I'm going to click it here. And yeah, here you go. So we can see the TensorFlow tutorial notebook here. And as you can see, that was actually designed in IWD 2021 as we discussed by TensorFlow and Pear's team. And we are going to go over this notebook today throughout this workshop. Now, coming back to the slide, let us learn first how to use your programming environment. So we are going to use Colab today. This is actually a Jupyter notebook environment that runs in the cloud, and it includes a free GPU. We'll use Colab for TensorFlow, but you can use it for any other open source library as well. So we are going to look into these things from the link I have shared with you. So just let me bring you back to the link so that you can check how the GPU works. So we are going to run a piece of cell to import the TensorFlow and to import the GPU as well. So I'm going to run this cell. As you can see, if we import TensorFlow, then we can take a print line to see whether it is imported correctly or not. And also we can check whether the GPU is enabled or not. So I'm going to run it, and you can run it from your Google Colab. Also, all you need is a Gmail account. It can take a couple of minutes. Oh, okay. So it is executed now, and once the execution is done correctly and there is no error, you can see a green check mark here. So as you have seen that I clicked on this play button to run the cell, and if you want to clear the output, you can click on these three dots and you can clear the output. If you want to make any changes in the code, you can write it here. And to make another code cell, for example, maybe you want to another piece of code, you can simply add a cell here. And as we don't need it, so I'm going to delete it. So this is actually a very quick and simple introduction of Google Colab. So we are going to move to the next part now. So in the next part, we are going to actually talk about TensorFlow, so and also neural network. So what is TensorFlow? We have imported TensorFlow, but what is actually TensorFlow? TensorFlow is basically an open source machine learning library, and it's a Python library with C++ backend. Usually you write code in Python, but you can also write code in JavaScript using TensorFlow.js. Now moving to the next part, we have to now import the dataset. And to import the dataset, we will need to know about our data. So let us see which data we have today. So we are going to build an image classifier on MNIST dataset, which is actually known as the hello world of computer vision. Although nothing in computer vision is simple. And this dataset contains 60,000 images of handwritten diseases, and it's popular for tutorials since it's small and it's easy to fit into the memory. Each image we have here has a 28 by 28 pixels and in grayscale, which means it's actually black and white images. So let's train a neural network and classify these images with the data set. Before that, we need to load this data, and for that, we need this piece of code. So let me bring you again to the browser. So if we see here that you can load the data set, but before loading the data set, you actually need to import an API, which is called Keras. So Keras is basically a TensorFlow's user-friendly API to define the neural network. So let us import the TensorFlow. And we have installed the TensorFlow before, so we have imported the Keras and also another library, which is matplot library. This is a Python library to plot the data set. And now let us run this cell, which actually will load the data. So let us check whether we have loaded the data and how is the shape of the data. So as you can see that the training images here, it has actually 60,000 instances, like 60,000 images, which everyone is of shape 28 by 28. That means it has 28 rows and 28 columns in the image matrix. And also let us test the shape of the test image. It has again the same shape. And let us check the levels. So if we check the levels of the training data, as you can see here, we have 504 levels. For example, if the image is 5, we have the level 5 for it. If it's the image of 4, we have the level 4 for it. Now let us go back to the presentation again. So you all just imported the dataset, but that was a clean and easy process compared to what it's like in the real world. So this may give you actually a sense of how much more complicated it can get outside of a tutorial environment like this. In practice, collecting a diverse data set that represents your problem well is one of the most important tasks in machine learning. And you will likely spend more time doing this comparing to the other steps. Now, let us move to the next part, which is creating the neural network. So we have to know about the deep learning before we create the neural network. So what is deep learning? Deep learning is actually a subfield of machine learning that involves writing and training neural network. Although powerful neural networks are one of the more advanced areas of machine learning, it takes a long time to gain intuition for how they work, and it's normal for many of the concepts we are talking about to introduce to feel opaque. And our goal is to give you a quick survey of the main ideas, and you can continue learning more at home. So what is neural network? To talk about a deep learning neural network, I actually picked here an analogy of deep learning from real life so that you can have like an easier view first, and then we will gradually move into the complex part. So if we talk about this analogy, you can see that here a model is trying different dresses from his clothes, and you can see that she's trying different poses, and the photographer here, she is determining when the pose is perfect to take a photographer. So in deep learning model, we can consider these traces and poses as input features, which will be provided as input to the model. And when the photographer is a take picture, we can consider this as the output of the model, and the pose they are trying, and when photographer is evaluating it, we can consider at the hidden layer of the neural network process of deep learning. And this is just an analogy to make the concept simpler, which we are going to see now. Now this is actually a neuron, and this is the basic building block of a neural network. So what does a neuron do is it's actually a binary classifier. For example, it takes some data as input, as you can see these X values. And on the left side, you can see that if you are training a neuron, we need to provide these X values and which are connected to some weights. So each X is actually multiplied by a weights theta, and these weights are initialized actually randomly by the neural network. Then it's learned with gradient descent. And what is gradient descent? It is actually a piece of code, but it performs the same thing we have seen in the previous example, like previous analogy, when the model and the outcome, like the photographer, both were trying to adjust in something to decide which will be the best pose for the to take the photograph. Now here, as you can see, that the neuron takes actually a linear combination of the weights, and finally it produces a score. So you could say that this score is either positive or negative. If the score is positive, let's say the class is aeroplane. If it's a negative, let's say the class is a car. So that's how we can like classify the images of different transports. And if we are considering some image as input, we will have some pixels. How? Let us see this into the next slide. So this is just another view of the neuron. One of the left side, you can see an image and the pixel values. So here we actually have RGB values of the image. That means it has red, green, and blue channels. So each pixels will have value from 0 to 255. Now, as you can see here, each pixels are coming to an input array, which is known as X, like just to give it as a name of the variable. And this is an one-dimensional array. Now these weights, these are actually randomly picked by the neural network, and we have to add some bias after taking the dot product of these weights and inputs. Finally, it will produce one score. So as you see, it's mathematical computation actually. So once we get the score, we have to decide a positive or negative value for it, and then based on the positive or negative value, we can find out the level. For example, here for positive, it's a plane. If we add another set of weights, for example, this one, it can produce maybe negative value. And for that, we can get another class, which is car. So as you can see that this and these are outputs. So we have multiple inputs, and for multiple inputs, we have multiple outputs. Now, for data like image or video, it's hard to identify the features. So it's not necessary you are gonna get 130.1 and minus 11.4 for all the images of planes and car, because they have different pixel values and they will give you different scores. So we need to normalize it to 0 and 1 or some other values to get the classes for different images. And this is one of the reasons that GPUs are popular in deep learning, because it is good for multiplying matrices. It's faster, and for processing image or video, like to classify image or video, we need the support from GPU. Now let's talk about the code. So here is another view with the code that corresponds to it below. So this is just, we are trying to build a neuron, actually one layer of the neural network with 10 outputs. Why? Because we have actually 10 neurons for 10 digits. We are here classifying digits from 0 to 9. Now, as you can see that for this image, like we have such image in our data set, we are going to take the input, which is actually pixels, and it will create a one-dimensional array from it. And for that, we need this code. So we actually have a 28 by 28 size of image, which gives us 784 pixels in total. So let us again move to the code. So if we come here, we can see that here we have an option for pre-processed data. So as we mentioned that our data is actually already pre-processed, so we can do a very little normalization. As we mentioned that the images have pixel from 0 to 255, so we just want to normalize it so that it can have value 0 and 1, dividing by all the images by 255. Now let us plot this image and check whether we have our data set. Yes, so we have our data set. So we have label for each of the training data, and this is just a portion of our data set which contains various digit images. Now it's time to create the layer. So as we have seen before that we can create one layer by providing the input shape. So let us talk about this first and run this cell. So we are now creating the very first layer of the neural network, and you can see that we have something which is called flattened, dense, and softmax. So let us see what these things actually mean here from the slide. So we were actually here. So talking about the next slide, as you can see that activation function. So what this softmax activation function is, this is actually a piece of math that that tries to convert the score into 0 or 1. Actually, it return a list of probabilities, And we are gonna not dig into the details due to the time limit, but you can take it later. Just keep in mind that the task of the softmax function is to give the probabilities, and you can see that it is applied in the last layer where you have the neuron, which is actually the outputs. Now moving to the next slide, you can see that we have another layer here. So basically in neural network we have different layers, and we need to determine how many layers we need also. So those are hidden layer, but we cannot um, we cannot add the activation or softmax function there. We have to add some another piece of code for activation, which is known as ReLU, which represent rectified linear unit, and these layers are called hidden layer. Now moving to the next slide, as we have seen about the nonlinear activation function. So ReLU is a nonlinear activation function, and you usually don't need to change this. We don't won't cover the details today, so we can proceed with this part. So in total we actually have this network now. So we have two hidden layers where we are applying rectified linear unit activation function, and in the last layer, which is the fully connected layer, here we are applying the softmax function. Now, as you can see, that building a model is pretty easy, right? Because you are going to write a couple of lines of code, around 20 or plus minus something. So the thing is, deep learning is something where the code is light, but the concept is heavy. This means you can implement a classifier like this very quickly, but it will take a long time to understand all the concepts. So let's see how does it looks graphically. Now it's time to train the model. But before we start training the model, let's take a moment to come back to the role that human perception plays. So as we mentioned that you have to determine some evaluation metrics for your model. So you have to ask some questions in mind. For example, how accurate is the model overall? How accurate is the model on certain digit? How confident is the model in a certain prediction? Is it predicting the 9 only correctly, or sometimes it's predicting 9 as 6? Just for example. And in this tutorial environment, since there is not an end user or use case, we are solving for per se, the stakes are actually pretty low for this example. But looking beyond this, determining the evaluation metrics is one of the most important thing you can do in machine learning. So if we talk about the data collection and labeling, that is the rigorous part that will consume more time. But this part is very important to say. It's not just a technical decision, but we need to think through the human impact of what we optimize for. Now let us talk about the gradient descent now. As we already know that neural network try to learn through gradient descent. So first we classify some images and then we calculate the error. Just like in the analogy you were watching, that the model was trying different poses with different dresses, and the output layer, which is the photographer, she was trying to understand that whether this pose is perfect or not to take a photograph. So after calculating the error, we figure out which way to adjust the weights in the network to make the error smaller, because your target is to provide better accuracy. So the TensorFlow handles this for you using an algorithm that is actually called Adam, which is a backpropagation algorithm, and this actually performs the same task you have seen in the analogy. So after that, it will adjust each words to a little and it will repeat it. Now the task of Adam is to optimize the steps automatically so that it is not too large or too small. Now we have to talk about a little bit of cross entropy also. So all neural networks actually trained by gradient descent, but and loss is a fancy word for your error actually. So we use actually cross entropy for the classifier. So what does it do is it in classification, cross entropy compares the distribution of the distribution the model predicted to the distribution we wanted. Now let us move to the next part. So this is the last piece of code we need to do for training the model. So here you can see we have used epochs. So let us know about epochs. So an epoch means that the neural network has used every example once to update its weights. The longer you train the model, the more accurate it will become on the training data. So that's why we need to careful about picking epochs, because if you do a longer training and provide 100% accuracy through your model, it will be suffering from overfitting. So let us again go back to our Colab notebook, and as you can see here that we have our data set so far. We have the pre-processing so far, and we need to now compile the model. So we have created our first layer 2, and now it's time to compile the model. So we are going to compile the model with this piece of code, and then we are going to feed the model with 10 epochs. So we have defined 10 epochs. For your different model, you can tune this parameter as you need, and we are trying to check the accuracy and loss while the training. As you can see that here the loss is minimizing gradually, right? And the accuracy here, it's increasing, which we actually want. So we want more accuracy, which is closer to 1. That means as close to as 1 possible. And we want to reduce the loss so that it becomes very closer to 0. So let's see how much we can obtain at epoch 10. So at epoch 10, we have 0.2508 loss, which is pretty lower, and we have very good accuracy, which is 0.93. So 93% accuracy is pretty good. Now let us evaluate the accuracy now. So we are evaluating it one test data. So this model is now getting one image of handwritten data, and we are going to get the test level from the model. As you can see that it is predicted at 93% accuracy, and the loss is also lower. So now make a prediction on a particular image. So we are going to test the prediction on a very particular image. Let's say the first image on the in the data set, and a prediction of this array is actually an array of 10 numbers. They represent the model's confidence that the image corresponds to each of the 10 digits. So let us print it, and as you can see that here the model has predicted 7 one digit correctly. So here we have another data set which is known as fashion MNIST. You can take it as an at-home exercise and practice yourself. Now let's go back to our presentation again. So talking about the next part, again we are gonna talk about this. So we are gonna now see how important it is to understand that the effect of the results. So uh, you have just gotten the flavor of a trained neural network. Sure, there were a lot of concepts, but it was only a very little amount of code. You don't need to do write like 1,000 lines of codes to build a neural network. That's okay. But to make it useful, we need to consider some other thing also. And we're going to talk about this from the next part of the workshop. And this is actually human-centered AI. So let's unpack it. By this time, you all have some understanding of how machine learning works, and you have even tried to see how to training the models and how to like build this neural network. But is it the thing that your customer is gonna see or your end user is gonna see? No, right? So what will this see? Actually, in practical setting, your customer will something from this to this. So something like this. Say if you develop a mobile app that uses image classifier models, it can like predict you something, or maybe you can visually search their environments. And as well as you know that machine learning is now in almost everything, like recommendation engines to really high stakes use cases like autonomous cars. But as more and more experience are built with machine learning, it's critical that we as product creators, designers, AI researchers, or developers understand the role we play in making users. We play in making users comfortable and feel in control of technology, and not the other way around. And that is one aspect of what we mean when we say human-centered AI. This is why the peer team works to advance the research and design of people-centric AI system. We are interested in the full spectrum of human interaction with AI, from supporting the product teams, building AI, to understanding people's everyday experiences with AI. Because it's just not about the technology, but the impact it has on us as human. And that's why we are here now talking about human-centered AI. So Pear actually has developed research tools and resources for building human-centered AI products, such as the People Plus AI Guidebook, which is just launched in May 2019 at Google I/O. So this guidebook is actually an open source framework, and it can help you make the AI product decision that are human centered. So due to time limit, we are not going to cover everything. The guidebook actually has 6 chapters, and we will particularly talking about the explainability and trust. So this is the chapter we focus on how users need to make decisions based on the predictions of your model, which boils down to how much should your user trust the AI system, and what are the ways to show the user the confidence associated with an AI prediction. You may notice that the second question is grayed out because we are not going to talk about this today. So let's talk about this spectrum. This is the trust spectrum. So on the one hand, you risk your user having no trust. So if they don't know where this prediction or recommendation is coming from, they just ignore it. For example, you might have seen so many social media application predicting your date of marriage, predicting your amount of income in maybe next 2 years. You sometimes simply ignore them because you don't have any trust on this application. On the other hand, if the user assumes that the system always knows the best and they don't question it, then you risk your user having too much trust. For example, if the weather prediction algorithm didn't have some other explanation rather than only one outcome, and you would go outside and trusting your application, and you saw that the weather prediction is totally different actually in country like Canada, it was a bad impact. So having too much trust is also not good. You are risking your customer in that way also, because AI products are based on statistics and probability, and the user actually shouldn't trust the system completely. So what does they need? What does the system we are building should do? The system we are building that should calibrate their trust, that is calibrate our customers trust. Based on the system explanations, the user should know when to trust the system's prediction and when to apply their own judgment. So to build calibrated trust, there are three key questions to ask of yourself or your team. Let's walk through each of these, which will also help set up all of you for a discussion, which we will see in a few minutes. So let us consider a situation where there is an AI-driven navigation app, and it may not be necessary to explain how arrival time is calculated for daily commute. However, if someone is trying to catch a flight, that's a higher stakes problem and less frequent than a commute. Now here, in this case, the system could prompt them with an explanation of these limitations, that there is a timing for recommending route. For example, if a user enters the local airport as their destination, let them know that traffic data only refreshes every hour. Now, another component is the presence or lack of system data impacting the feature's confidence. What does it mean? Let's take an example. If a music recommendation app claimed to cater to all music lover, but the feature was not trained on death metal, that would really erode trust of many users. So before we claim something, we need to also talk about our data, and we have to look into the data too. So next one is what users knowledge is impacting trust in this situation. So as we have already discussed about this a little bit during showing the trust spectrum, if your users are subject matter experts in the feature domain, they will be scrutinizing the prediction much more heavily versus a user that is not an expert and who may end up over trusting a recommendation because of lack of prior knowledge. So let's get into our discussion exercise now. Think about a time you have used an app that provided predictions or recommendations, and what user knowledge impacted trust in this situation. For example, did you trust this application 100%, or is it like you didn't trust this application a bit, or it was like that there was something in the application that helped you to calibrate the trust? So think about it and put your answer in the chat. We are going to discuss about this at the end of the session. Now we are going to talk about displaying model confidence. So now we have seen that how can you help your users to calibrate trust in your machine learning driven feature. Then this brings us to if or when or how we should display the model confidence for our users. So first, confidence level or model confidence is actually a statistical measures of how certain prediction or outcome is. For example, if you remember at the end of the MNIST tutorial where we printed the model's confidence that the image correspond to each of the 10 digits, and you saw which level has the highest confidence value, right? We saw 7 has the highest confident value. So we need to think about this frequently, repeatedly, through some trial and error, that what can be beneficial for our end users. And the confidence level actually isn't impactful if it doesn't make an impact on user decision making. Now let us see some of the ways that has been actually proposed in the guideline book, and it includes categorical or presenting the n-best options, or even presenting the percentage of accuracy of the prediction and data visualization to explain the prediction of your model. So let us take one by one. Now the categorical visualization, it actually categorizes the confidence values into buckets such as high, medium, low, and show the category rather than the numerical value. And this is an example from Gboard, which offers swipe typing and predictive text. This is slightly modified version of categorical, where the best match featured is in the center, and good matches and the low matches are on other sides. The next one is the n-best option. Here, actually, n is a certain number, like maybe top 1 or 5 matches in this n-best example. As you can see in this Google Translator example, it suggests the most confident translation followed by other options. Next comes the numeric option. It's very common. However, you have to be careful here because numeric confidence indicators are risky, as it presume your users have a good baseline understanding of probability. And you have to make some additional consideration here. For example, you need to put some information about the context maybe, because if your user is a novice user, they may not know whether a value like 80% is low or high for a certain context. Then comes the graphic-based indicators of certainty. For example, a financial forecast could include error bars or shaded areas indicating the range of alternative outcomes based on the system's confidence level. And here in this example, we have visualized a prediction of whether or not a kind of diabetic retinopathy is present in the image above. Now, we have actually talked through a handful of these design patterns for how you can show model confidence to your users in a way that is clear and actionable. So let's try applying that, what we learned in this in the next exercise. So imagine you are building an image classifier to help your users to identify the breed of a dog. For example, whether it's a lab, husky, poodle, etc. And think about the confidence display patterns that might be useful for your users. You can pick any from these four and type the name in the chat. So this was the similar thing that while developing a Google Lens, the team has to think about, and they choose the N-best option. So when a user pans their phone's camera across something, say a dog, the Google Lens will show the top match, and if the user swipes up, they will see the lower confident matches too. Now, to wrap up what we have learned from this chapter of explainability plus trust from the People plus AI guidebook, um, you actually need to consider how the stakes, system data, and user knowledge can be used to calibrate the trust of the user. But try to make it confirm that you are taking some time to think about how, when, and why the model confidence score will be beneficial for your user. Here are some resources. We are going to share these resources with you so that you can use this later. And this is another option of representing explainability of the model. Nowadays this is used a lot in AI research because this is very new, so everyone is now kind of trying to add explainable AI to their prediction, to being the trust in the AI model. And as you can see here, this is actually an output of Lime tool, which defines the reason responsible for predicting an image as a dog image and an image as image of the cat image. So you can see the region are highlighted which are responsible for the prediction. So thank you everyone for taking your time to attend this workshop, and we would request you to fill out this form to provide your feedback.